This is the Earth Science Classroom. Welcome back to the video and channel. This channel looks at everything geoscience, atmospheric science, and earth science videos, also including astronomy as well. This video is wave erosion. It's part of the weathering and erosion playlist. Also can be in the geomorphology playlist and rocks playlist. And this video in particular is looking at defining and discussing what wave erosion is, where and why does this occur, and when it occurs, what features are created by this wave erosion that we can see on our coastlines. So we got some amazing pictures here of some coastlines and some breaking, plunging waves, and this picture in particular right here. Now, this picture is of a cliff that is part of the Chapelporth Beach in Cornwall, England. Now, it's special for me personally because I grew up about 10 minutes away from this beach and spent 21 years of my life growing up in England, in Cornwall, with the most amazing childhood, playing soccer, playing football, bodyboarding, surfing, swimming in the ocean. I mean, every summer when it was schools were out, when it was summer holidays, I would spend the time at the beach. When I got older and I could be more confident in the ocean and bodyboarding, I would be out in the ocean, during the winter swells or the storms when the temperature of the water was freezing cold. And I grew up watching the ocean and land interact with this beautiful tidal range and beautiful high cliffs. Surf pretty much all year round. Wasn't the greatest surf, but it's what we had, and a beautiful sandy beach that was exposed during low tide. And it's just a gorgeous place to grow up, very picturesque. It's very close to my heart, this video. So what is wave erosion? Now, it is the power, the energy, and the force that is within the ocean waves. So it's the orbital motion or ocean particle, water particle energy that flows through the ocean, and eventually it's going to interact with some sort of coastline or a coastal zone. So this energy that's being transferred across a given distance of ocean is driven or derived from wind, which we can take from a difference in pressure along the surface, which is low and high, and the movement of air particles between high and low pressure, again derived from really the temperature differences on the Earth's surface between the equatorial regions and the poles, and the willingness for the Earth to move and transfer heat from north to south. So wind really is the driving force, but also you have tides as well, and the geomorphology, I'll put GeoM, of the coastline, which will dictate the energy and how it's transferred. So whether it's going to be a different type of wave, spilling, plunging, or just surging wave, versus a cliffed coastline versus a flat or more sandy beach coastline, that will dictate also how the energy is transferred. So the energy goes from the ocean and it gets transferred and basically hit, or arrived at the coastline. And the coastline is obviously solid rock in terms of a cliff, or unconsolidated material, which would be a beach of some sort. It could be a pebble beach, sandy beach, various different coarse levels and size of sand, but you have a beach of some sort. Now, this energy will be transferred into the coastline and beach, and what happens is you do get, obviously, the weathering by the sheer force of the waves, but you get the transportation of the weathered material using the waves, ocean, and currents. So we can also add in here ocean currents, which again derive from wind, but the deep ocean currents as well that could carry some materials is driven by temperature and salinity differences. So that's really what the wave erosion is, and it's basically located around the coastlines of the planet. So before we get into the actual particulars of the erosional features and list them out and show you diagrams, it's clear to state that weathering plays a major role in this environment, with the sheer force of waves impacting the coastline or the rock or the sandy beach. You're going to have the mostly mechanical, or sometimes we call it physical, weathering taking place along the coastline. That would enable erosion to take hold and remove and transport that weather material away from that location, usually with the swash and backwash or some sort of rip currents, or even the removal into what's called a submarine fan, which is basically a deposition environment in deep water, whereby the sediment has been deposited and fallen through gravity down to a deeper ocean floor, and it accumulates in a fan shaped. So, this is the movement, and it fans out on the ocean floor like this. So it looks like a submerged river delta, basically, of sediment. So the erosion obviously needs the weathering to take place, but obviously with waves being of very large force, you're going to see a quicker, more effective weathering process. In some cases, you still could have chemical weathering as well, but it is mostly going to be mechanical and physical in nature. All right, so in terms of features, I have this generic coastline here on this drawing or schematic. And we have the coastline right here. All right, here's the coastline. And here is our rocky material and our bedrock, and going into the ocean floor right here. We have our ocean right here, and we have our direction of ocean swell and prevailing wind. Okay, we have how our layer of sediment could be either shallow or deep sediment accumulation or deposition environment. We have our high tide mark, which is this line right here. We have our low tide mark, which is the line, which is dashed line right there. And this would give us our intertidal zone or area, intertidal, which would provide different environments, and it would provide different types of weather and erosion and features because of the exposure to the atmosphere and in between the tidal cycles, whether it's diurnal or semi-diurnal tides. So again, this is linked with weather and erosion because you can't have erosion without weathering, and you're basically removing a lot of material from this section of cliff. So right here we have our lovely, in orange right here, we have our lovely wave cut platform. It's right there. What happens is the ocean, during high tide or storms, the ocean rises and it's going to basically weather and erode a section of the lower cliff based on consistency and intensity and raw energy. Ocean waves can produce around 2,000 pounds per square foot of force applied to an area. So that's a ton of force, and that's a normal wave generally during any kind of storm conditions or hurricane conditions. You might have double or quadruple the amount of pounds per square foot force being applied to coastlines and beaches. So these natural processes hold a great deal of energy, and it can be very effective at breaking down this rock, especially the rock is not very resistant or a certain type, let's say metamorphic or igneous, but rather it's sedimentary. It will be eroded pretty quickly. So wave cut platform, this can be part also of a wave cut notch, which is right here. The notch is right here. The platform is right here, the raised area, and this can be part of a bench as well, a wave cut bench, which is a raised area, and the sea levels dropped off. But this can be part or sections of what's called a marine terrace, which is kind of like a step-by-step lowering of the coastline, the rocky coastline, and you had this like flat plateau, then a little drop, flat plateau, drop, based on the erosion of the water level. And the water level could be up here, then in a few thousand years it could be down here, and then further down here, thus exposing these different steps of the coastline, going from the cliffs down to the current shore and beach face. So this is part of the edge between the cliff and the ocean, which is the marine terrace, which includes the bench, the wave-cut platform, and the wave-cut notch. The notch is right here, and this could cause this area to fall down through gravity, which is rockfall, which is mass wasting, and can be very dangerous. So next thing that can form is obviously a sandy beach. So you could have a sandy beach right here, and the movement of material, sand, sediment, which is unconsolidated, could be transferred onto the gradients, various slope gradient of the beach and the shore face, and the sand can build up and provide a beach, and different levels of beach, different sediment levels of beach. And this can be exposed to, if it's a larger, more exposed coastline to the ocean, you could have longshore drift, you could have longshore currents, riptides, which would transfer the sand along parallel to the coastline to different areas where it would be deposited. And you might get spits occur, or various offshore barrier islands, or depends on how shallow and deep the water is. If you have a large enough area or force of water, you might erode a small area, weather and erode a small opening, and that would increase the amount of water in, so thus making this area larger, which would create a little hole in the cliff, which we call a sea cave. It can also start to erode in a little half, semicircle kind of angle, kind of shape, and this would be called a sea cove. And that would expose areas that are more resistant to areas that are less resistant and are weathered and eroded quicker, thus leaving this kind of sticking out part of the land or headland, which is more resistant, and that over time would have its own features carved into it by the water and by the wave action, and the original coastline could be actually here. And over time, it has retreated inland. And what happens is the more resistant rock is kind of staying there. The rock that's less resistant would be eroded, leaving various bays and coves and inlets. And this headland would be kind of protruding out into the ocean, and it would take the full force of the waves. Now this would create what's called wave refraction, which would bring the waves around. Thus, it would break down areas of the cliff, so the cliff would continue out like this, and over time, this wave refraction has concentrated and focused its energy on this area right here, thus weathering and eroding this area, allowing a collapse of the arch that was created, okay, leaving a gap between this rock, which is smaller, being eroded down, and this taller, more column rock right here. Now this is called a stomp, which would eventually weather and erode back in, small enough that the ocean then consumes it again, or based on the sea level. And this one is called a stack, basically a larger version of a stomp that has been eroded less and is more rectangular in dimensions and shape. And then we have this natural arch, this arch right here. And there is the wave refraction energy causing this kind of sea cove to pass right through and create this arch, this rocky arch, that if continued with the erosion, like with the stack and the stomp, this archway right here would actually collapse in, be transported away through the riptides or longshore current or storm systems, and leave a new stack right here to accompany this one. So certain coastlines like Australia, they have the 12 apostles, which are various sizes of stacks and stomps along a certain coastline. And then this this headland would be smaller based on how far it retreats. It would just become more of a flatter coastline or be a smaller protruding headland. With the sea cave right here, you might have the water erosion, the wave erosion going into the cave and slowly but surely eroding the inside of the cave, creating a nice big void. And what happens is the water energy has to go somewhere, so it would find areas of weakness, cause fractures and joints, and eventually come up and make a little hole on the surface. And what will happen is in goes the wave action, and they'll blow out of this hole as like a little, like a whale does to try and breathe on the surface, and we call this a blowhole. So to overview this picture with a cliffed coastline, lots of different factors would come into play with the complexity of what this coastline would look like, how it's going to change over time based on sea level, which is ice ages, or age, or the ice ages, and glacial, looking at obviously the climate, prevailing wind, swell patterns, then wave patterns, the topography of the beach, the gradients. We're looking at the geology of the rock in terms of how resistant the rock is to the wave action, and depends on the intensity of the waves, and any kind of abrasion and hydraulic action, and the material being pushed and forced against the cliffs. And obviously the time which is how long this process is going on for. The longer it is, the more it's going to wear down, weather, and obviously erode. So time is a huge important factor, which would link up to tectonics and how long that coastline would be there for at a certain level, at a certain elevation, and obviously the sea level, which again is back down to ice ages. So a lot of different variations could occur, which would create different kinds of coastal features, erosional features that dot around the world's coastlines. Some are very dramatic and impactful. Some are more subtle and need to get close up to see them. But it is a fantastic, beautiful subject, and ever changing, ever adapting to all these conditions. This is the Earth Science Classroom. Thank you for watching. I hope you enjoyed the content. Check out more videos on our channel, and don't forget to subscribe. Thank you again.